In this video, we're going to be diving deeper into the periodic table and learning about the trends that the periodic table follows. So remember, the periodic table, it can be composed of ions, either positive or negative. Part of this is determined by the valence electrons. Remember, we learned about these in our last unit, where the pattern is 1, 2, 2, 3, 4, 5, 6, 7, 8. Now the charges follow the 1 plus, 2 plus, then we skip the center, 3 plus, then we also skip the carbon column, 3 minus, 2 minus, 1 minus, 0, which I sometimes call zip. So I have this little saying, 1 plus, 2 plus, 3 plus, skip, 3 minus, 2 minus, 1 minus, zip, is how I remember the charges on the periodic table. So when it comes to ions, we have cations, which are positively charged. They're formed when we lose electrons, because remember, electrons have a negative charge, so when you lose a negative, it becomes positive. Metals form our cations. Silver always has a 1 plus charge, and zinc and cadmium always have a 2 plus charge. You are responsible for having those 3 transition metals memorized. Then we have our anions, which are negatively charged. They are formed by gaining electrons, because once again, electrons have a negative charge to them, so when we gain a negative, it becomes negative. They are formed by nonmetals, and keep in mind our noble gases are not either cations or anions because they never have a charge. So why do atoms even form ions? So those valence electrons that we've already talked about are those outermost electrons. Of all the electrons that an atom has, these are the ones the farthest outside. And they are all trying to meet what is called the Octet Rule, which is a chemical rule of thumb that states that atoms of main group elements tend to combine in such a way that atoms have 8 electrons in their valence shell, giving it the same configuration as a noble gas. So that is what all of our elements on the periodic table are searching for. So some of them give up electrons to make that happen, and some of them take electrons to make that happen, to get that 8. The exception to the octet rule is hydrogen and helium. They only want a duet, meaning 2 valence electrons. Once again, valence electrons are gained, lost, or shared in order for this octet to be achieved. So this brings us to polyatomic ions. So a monoatomic ion is an atom with an overall charge consisting of just one element, mono meaning 1. Meanwhile, a polyatomic ion, poly meaning many, is a group of elements with an overall charge. So polyatomic ions act as if they are a single unit. They go together, they cannot be separated from each other. And as a unit, they have a charge. You will notice on the back of your periodic table, you have a list of common polyatomic ions, and you will be given the same list on any test we take. Some examples of polyatomic ions that we will be frequently using. You don't need to memorize them, but you can see what I'm talking about. They have multiple elements in them, like ammonium has nitrogen and hydrogen, but it then also has a charge associated with them. Polyatomic ions can be anions or cations, although they are most commonly anions. So diatomic molecules are 2 atoms of the same element that are chemically bonded together. This includes hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You are responsible for knowing the 7 diatomic molecules. I remember them by the name Brinkelhoff. You'll constantly hear me saying that this is a Brinkelhoff, and that is what I mean. B for bromine, I for iodine, N for nitrogen, Cl for chlorine, H for hydrogen, O for oxygen, and F for fluorine. You may also notice if you look at them on your periodic table, they form a 7 if you're looking at another way to memorize them. So you're going to see a lot of chemical symbols this year, and it's important you know how to count atoms. So if there are no numbers by the symbol of an element, we assume there's only one. So if you just say Na, that means there's just one sodium. If you see MgO, that means we have one magnesium, one oxygen. So no number means one. A subscript is written at the lower right corner of a chemical symbol. If there is more than one, then that number is used. For example, H2 means we have 2 hydrogens. Li2O means that I have 2 lithiums and 1 oxygen. A subscript outside an atom multiplies all the elements inside the parentheses by that number. So for example, if we have Mg3PO4 2, that 2 only multiplies what is inside the parentheses. So we have 3 magnesiums, 2 phosphoruses, and 8 oxygens. A coefficient is a number written in front of a chemical symbol or in front of a chemical formula, which indicates the number of atoms or molecules in the substance. So a coefficient multiplies the entire thing by that number. For example, 3C means I have 3 carbons. 2H2O is telling me I have 2 waters, which means I have 4 hydrogens and 2 oxygen. Counting atoms really isn't that bad. I know you can do it. So why don't you take a second, pause this video, and figure out how much of each element you have in the following 8 chemical equations. Pause this video and come back when you're done to check your answers. Let's see how you did. For our first one, you should have gotten 1 sodium, 1 carbon, 3 oxygens. Pretty simple. 2 took it up a little bit, but you should have gotten 3 calciums, 2 phosphoruses, and 8 oxygens. 3 should have been 2 potassiums, 1 chromium, 4 oxygens. 4 threw a coefficient in the front at you, giving you 3 bariums and 6 chlorines. 5 had you making sure you could count across a whole atom with 1 nitrogen, 7 hydrogens coming from the 4 hydrogens here, the 3 hydrogens there, 2 carbons and 2 oxygens. 6 was a real tough one. You had your coefficient in front and you had those parentheses, so you wanted to make sure you got everything right. This gave us 8 aluminums. 2 times 4 is 8. This gave us 12 carbons because this 3 meant we had 3 carbons and then we multiply it by 4 for 12. And 36 oxygens because 3 times 3 is 9 oxygens times 4 is 36. 7 was more simple with 2 leads, 2 nitrogens, and 6 oxygens. And then 8 was a lot like 6 in that you had a lot of things you had to think about, coming in with 4 nitrogens, 16 hydrogens, 4 chromiums, and 14 oxygens. How did you do? Is there a pattern to anything you missed? Pay attention to what that pattern is and focus on things you might need to ask questions on later. So this brings us to the periodic trends. Now there are 5 periodic trends you are responsible for knowing, and that is atomic radius, ionic radius, ionization energy, electronegativity, and metallic characteristics. So let's dive in. The first is atomic radius. So the atomic radius is defined as 1/2 the distance between the nuclei of an atom bonded together. So you can see our picture right there. The radius decreases going across a row, so from left to right it decreases, and it increases going down a column, so from top to bottom it increases. This is a picture. You won't ever be provided with this, but this is showing you what I'm talking about. You can see as we go across, they get smaller, but as we go down on any given column, they get bigger. I refer to atomic radius as a 930 trend because if you think about it with the arrows pointing in the increasing direction, it looks like a clock is reading 930. So we know we increase on the left side of the periodic table and we increase on the bottom of the periodic table. So once again, atomic radius increases as we move from right to left and it increases as we move from top to bottom. So where is the element with the largest atomic radius located, and what element is it? That means it's going to be in our bottom left-hand corner, and you're going to see that that is francium. So why is the atomic radius trend like this? So why are atoms larger as we go down a group from top to bottom? So atoms are larger because at the higher energy levels, the more orbitals an atom has, the more electrons, which means they're going to be bigger because they need more orbitals for those electrons to go in. That probably makes a lot of sense to you. But then why do they get smaller as we go across? Aren't they getting more electrons too? The reason is as we move from the left side to the right side, we're getting an increased nuclear charge, meaning we have more protons. So those protons hold the electrons in more closely. Positive and negative are reacting with each other to pull them in more closely. So they get smaller as we go across. All right, based on knowing that atomic radius is a 930 trend, meaning once again, increases to the left, increases going down, I want you to pause this video and answer the following questions on your sheet. Come back when you're finished. All right. You were first asked which of the following has the largest atomic radius. First, between cobalt and nickel. And if you were looking at a periodic table, you should have selected cobalt because it was to the left of nickel, making it bigger. Next, you were asked phosphorus versus nitrogen, where you should have chosen phosphorus because it is farther down on the periodic table than nitrogen. And then between potassium and oxygen, you should have chosen potassium because it's farther to the left and farther down, making it the clear winner. This asks you to, next you were asked to list 3 elements in order of increasing atomic radius, meaning the first one should be your smallest and your last one should be your largest. Up first, it should have gone fluorine being the smallest because it's all the way up at the top right side, then carbon, then gallium. On your next one, it should have been iodine as your smallest, then gold, and then last barium. Then you were asked to list them in decreasing atomic radius, meaning the first one should be your largest, and the last one would be your smallest, with a correct answer of sodium being our largest one, aluminum being next, and then sulfur being our smallest atomic radius. How did you do? If you got these right, great, let's keep going. If you didn't get these right, go back and look over atomic radius again, see if you can clarify some things for yourself. Which brings us to ionic radius, the radius of an atom once it becomes an ion. A cation has a smaller radius than its atom, so if it has that positive charge, it lost electrons, it is going to be smaller. And an anion has a larger radius than its atom. Anions gained electrons, therefore they got bigger than the original atom. This one is pretty simple. You can see once again a picture of this happening where our negative charges are bigger for the most part than our positive charges are. Ionic radius really isn't that bad. I think you already probably have the hang of it. So this question asks you which of the following has a larger radius and then gives you 2 choices. Why don't you pause this video and come back when you're done. Up first, you were asked about the calcium atom, no charge, versus the calcium ion, which has a 2+ charge, meaning it lost 2 electrons, making it smaller, which means our calcium atom is the bigger one. Then you were asked about manganese atom, or manganese ion. The manganese atom has no charge. Manganese ion has a positive charge, which instantly lets us know that we're talking about the manganese atom. As far as selenium is concerned, we can look on our periodic table and see that the selenium atom, while having no charge, its ion is going to have a 2- charge, meaning it gained 2 electrons, making it bigger. Then we have the chlorine atom, or the chlorine ion. The chlorine ion has a 1- charge, making it bigger. Our next periodic trend is ionization energy. Ionization energy is the energy required to completely remove an electron from an atom or ion. This is called a 3 o'clock trend because it increases going towards the top and it increases going to the right, so it looks like the hands of a clock when it reads 3 o'clock. And just to note, we ignore noble gases for ionization energy because they don't become ions, which is what happens when you remove an electron from an atom. Here is a picture showing you all of the different ionization energies out there. Once again, you're not going to be given this or need it, but just to show you how this trend works, you can see way up here, helium has our absolute highest ionization energy. Meanwhile, francium down here has our absolute lowest one. So knowing that it is a 3 o'clock trend, increases to the right, increases going up, I want you to pause this video and answer the following questions. Come back when you're done to see how you did. All right, as far as largest ionization energy, we have nickel because it is farther to the right than cobalt. We have nitrogen because it's higher up than phosphorus. And we have oxygen because it is farther up and to the right than potassium is. Next, you were asked to put the following in increasing ionization energy, meaning the one with the highest ionization energy would be first, and the one with the lowest ionization energy would be last. So that put gallium as our smallest, then we moved up the periodic table to carbon and finished off with fluorine. As far as barium, iodine, and gold is concerned, barium has our lowest in that group, gold is next, and iodine has our highest ionization energy of that group. Then last we had aluminum, sulfur, and sodium, where sulfur would have had the highest ionization energy of that group, aluminum has the middle, and then sodium has the lowest ionization energy of that group, putting them in decreasing ionization energy. How'd you do? If you did good, let's keep going. If you didn't, go back and review ionization energy again. Our next periodic trend is electronegativity. So electronegativity is a measure of the attraction of an atom from the electrons in the chemical bond, so how attracted they are to each other. Like ionization energy, electronegativity is also a 3 o'clock trend, meaning it increases from the bottom up to the top and increases from the left to the right, and we also are still ignoring the noble gases because they don't attract ions. Here is a periodic table showing the electronegativity values. We're going to be revisiting this later in the semester, but you can see what I'm talking about, where fluorine over here has a super high electronegativity. Meanwhile, cesium down here has a really low one. Based on it being a 3 o'clock trend, I want you to pause this video and come back when you are finished. All right, if you felt like you were having a little bit of deja vu when you were doing this, you probably were. So since ionization energy is a 3 o'clock trend and electronegativity is a 3 o'clock trend, the answers are going to be the same. Where nickel has the largest electronegativity, so does nitrogen and oxygen. If we're going to put them in increasing, we're going to have gallium, carbon, and fluorine. Then we're going to have barium, gold, and iodine. And if we put them in decreasing order, it would be sulfur, aluminum, sodium. If something has the same trend, they're going to have the same answers. So it really just comes down to memorizing what's a 3 o'clock trend versus what's a 9:30 trend. So as I already mentioned, ionization energy and electronegativity have the same periodic trend, 3 o'clock. This is because the electrons of smaller atoms are closer to the nucleus, stronger attraction, and that makes them harder to pull electrons away. Larger atoms, their valence electrons are further away, and it makes them really easy to steal. So that's why atomic radius is a different trend than electronegativity and ionization energy are. However, atomic radius does have a friend trend as well, and that's its friend is in metal reactivity / metallic characteristics. It is also a 9:30 trend. where the metal reactivity increases as we move from the right to the left, and it increases as we move from top to the bottom, once again looking like the hands of 9:30 on the clock. Just like with atomic radius, our most reactive metal is going to be francium down in that bottom left corner. Now keep in mind, this makes a lot of sense because our non-metals live on the right side of the periodic table. So they don't even factor into metal reactivity because they're not even metals. This is an activity series which we will be using once again later in the semester, and it ranks our metals as far as their reactivity is concerned. If you look on the back of your periodic table, you will see one as well. All right. Knowing that metallic characteristics are a 9:30 trend, I want you to pause this video and come back once you have answered your questions. All right, let's see how you did. Once again, if you maybe felt like you were having deja vu, you were, because since it's a 9:30 trend, just like atomic radius was, your answers should have ended up being the same. Where cobalt has the most metallic characteristics, phosphorus is going to have the most metallic characteristics, and potassium is going to have the most metallic characteristics. Putting them in increasing metallic characteristics order, we would have fluorine having the least, carbon coming in next, which since they are both non-metals, that makes a lot of sense that they're going to be low. And then gallium is actually a metal, making it the most metallic. With barium, iodine, and gold, iodine is going to be the least. Once again, it is a non-metal, so it is not going to have many metallic characteristics. Gold is a metal, but it's kind of in the middle. And then barium has our most metallic characteristics. Going in decreasing order, so starting with the strongest, that's going to be sodium, then it's going to be aluminum, and then last sulfur. Once again, sulfur being a non-metal, so it's going to make sense that it has the lowest. Our non-metals will always have lower metallic characteristics than the metals are going to, because they aren't metals. Whoa, that was a lot. But I don't think it's really that bad once you get a handle on 9:30 trends and 3 o'clock trends. So here summarizes everything we've just spent the past 20 minutes talking about, where you can see how things increase and decrease moving around the periodic table. Now, maybe you aren't a visual person like this, you're more of a chart person. So I made a chart for you too. Remember, periods go across the periodic table and groups go up and down. So in this chart, it's showing you that atomic radius increases going down, while ionization energy and electronegativity increase going up, and metallic characteristics increase going down. Same thing within our groups. So write these down in your notes and come to class ready to keep working with our periodic trends.